Yeah, over to Bhumika and Astha. You may start.
A very good evening to all of you present here. Welcome all. Today we are in the second day of Curry Leaf Days 2023, which is organized by Curry Leaf, MTTS Alumni Association, in collaboration with MTTS Trust. So today we have with us Dr. Prahlad Vaidyanathan. Welcome to you, sir. Now, Astha will tell you more about Dr. Prahlad Vaidyanathan. Over to you, Astha.
Dr. Prahlad Vaidyanathan is an esteemed associate professor of mathematics at prestigious Indian Institute of Science, Education and Research, Bhopal. With a distinguished academic background, he earned his PhD from the renowned Purdue University. His research interests are operator algebras and K-theory, to which he has widely contributed. His profound expertise and dedication to advanced mathematical knowledge have earned him a prominent place in the academic community. Today, he is going to deliver a talk on expander graphs and groups, which will include exploration of expander graphs and their significance in the number network theory. Additionally, the abstract alludes to the utilization of group theory, highlighting the connection between abstract algebra and the construction of expander families of graphs. Over to you, Bhumika.
Thank you. We are really glad to have you, sir. Before we start the talk, I would like to give some basic instructions to all those who are watching it live on YouTube as well as on the Zoom. So, people on Zoom, if you have any questions, kindly feel free to ask them. You have the raise hand button in the Zoom. Kindly utilize it and don't kindly refrain yourself from unmuting unless you are asked by someone. Also, the people who are watching live on YouTube, kindly, if you have any questions, drop it on the comment box. We will make sure that it will be asked to sir. Yeah, over to you, sir.
Okay, thank you. Thank you, Bhumika, Soumya, and all the other organizers. It's nice to be here. MTTS was a big part of my life a long time ago, and it's nice to give back some of what I have learned from there. So today I'm going to talk about an interesting topic. It's not directly related to what I do, but I thought it would be a nice exploration with all of you because, you know, we all have different backgrounds. So I thought it would be nice to talk about something that is reasonably accessible. The topic is what are called expander graphs. These are a certain family of graphs and their connections with group theory. So before I talk about what that is, let me start with, so this is the contents. I'll talk about networks and how they are related to expander graphs. Then I'll talk about how group theory can be used to construct graphs. And then I'll talk a little bit about how expander graphs come about, why certain groups are used to construct expander graphs. And that bit may be a little technical, but I hope that everyone should follow along broadly what I'm going to say. So let me start with the basic idea of what I want to talk about, networks. So a network is, you should think of it as a finite number of vertices, where vertices represent humans. And each pair, some pairs of humans are connected by edges, which you can think of as wires. So you can think of it like a telephone network or the internet or anything like that. And in mathematics, this idea is captured in the notion of a graph. So for those of you who have not seen it, a graph is a pair, G, which consists of a set of vertices and a set of edges. And the vertices are just some set. There is no other structure to it. And the edges consist of some number of pairs, x comma y, where x and y are vertices. So I have drawn two pictures over here of graphs, and naturally you can draw any number. I should mention that the graphs here are undirected, which means that if I can transfer information from one vertex to another vertex, I can transfer information back. So there is no direction involved in this data transfer. Okay. So this is what a graph is. Now, what I want to sort of explore, this is a little vague at the moment, we'll make it more precise, is what we mean by a good network. So a network is basically a collection of people who are connected to each other by these edges. And what we want from it is sort of four conditions. One is it should be a cost-effective network. Namely, edges, which are wires, they cost money. So we want to minimize the number of edges. Okay. And what I mean by that, we'll talk about shortly. We also want it to be connected, which means that if I give you any two vertices, there should be not necessarily one edge that connects the vertex to another, but there should be a sequence of edges which take you from X to Y. In other words, you might have to go through another vertex, but that's fine as long as you can go from X to Y, and this should be true for any pair of vertices. The last two conditions are necessarily a little vague at the moment. We want the network to be fast. Namely, if I take any two vertices, I should be able to traverse the distance from one to the other in a relatively short period of time. Okay. So I'll make sense of what distance means in a graph shortly, but this is what we mean by fast. The last one is even more difficult to make precise. We want it to be reliable. What that means is, let's say I have a network consisting of two chunks of vertices which are all connected to each other, but there is only one edge connecting this chunk to that chunk. Then the moment I break this one edge, the network collapses because I can no longer communicate from, say, one city to another city. Imagine two cities and only one highway connecting one to the other. This would not be desirable because everything depends on that highway, and that is it puts too much pressure on a single edge. So we want a network where there may be multiple ways to go from one point to another point so that there are no bottlenecks, like in a traffic jam. You don't want traffic jams. Okay, so that's what we mean by reliability. And the last thing is we want a model which is also scalable, which means we want to not just construct one network, but we want to construct families of networks, a sequence of networks in such a way that for each network should independently be good. Also, as the network grows, as I add more and more vertices to it, the network should remain cost-effective, fast, reliable, and so on. Okay, so all the conditions I had on the previous slide, I want them to be maintained as we grow the network. Okay. So this is, you can think of it like a question of how do you plan a telephone network in a city or something like that. Okay, that's roughly what we are looking at. So we are looking for 5 conditions. These 4: cost-effective, connected, fast, reliable, and finally we want a scalable one. Okay, and by scalable I mean a sequence of graphs where the number of vertices is growing to infinity. Right. So I will say one thing over here. If anybody has any questions, I request the moderators to kind of let me know because I'm not able to see the hands raised and all that. So I will leave it to you. That's
Sure.
it. Yeah. Okay. So this is what we want out of our network. Now, the first thing you will notice is that there is a little bit of a tension between two of the conditions. One is we want the model to be scalable, and the other is we also want it to be cost effective. Now, if you keep adding vertices, and naturally you want the vertices to be connected to other vertices, you want a connected network. What do we mean by cost effective in that context? Because you can't just put a condition that says the number of the number of edges should be finite. That's not meaningful because we want the number of vertices to grow. So what we do is a little more precise. We say that, okay, so how do you minimize the number of edges even though you want the number of vertices to go to plus infinity? Turns out there is something you can control, which is the degree of the vertex. So if you take a vertex and you look at the number of edges coming out of it, that's called the degree of the vertex. Okay. Now, we cannot require that the total number of edges is controlled, but we can require that the degrees are all uniformly controlled, which means that there should exist a single number d. such that the degree of every vertex is less than equal to d. Okay, so it's like saying everybody in the network has at most 5 neighbors, but the network can be huge. You can have 10,000, 50,000 people, but each person has only 5 neighbors. Okay, so this reduces the cost in a sense. It makes it so that you only need a minimal number of wires, but it allows you to keep it scalable. So you can grow the number of vertices without breaking this requirement. And what we will do for simplicity's sake is we will assume that all vertices for all the graphs we are constructing will have the same degree. In other words, there exists a single D such that the degree of every vertex is equal to D. Fine. And such a graph is called a regular graph. And when you want to specify what that D is, we call it a deregular graph. So you can have 2 regular graphs, 5 regular graphs, 11 regular graphs, etc. Okay. So this is the kind of graph we are going to look at. We're going to look at regular graphs with all these conditions that I was talking about. Okay. Now, how do you measure fast? Now, fast is a relatively easy thing to talk about, but exactly how we want to control it, I will come to in a second. So suppose I take a graph and let's say I take 2 vertices. I look at the number of paths from X to Y, namely all the sequence of edges I have to go when I start at X and end at Y. And I look at all these paths, and I look at the path with the least number of edges. Okay. This is called the distance from X to Y, and I will denote it by rho of X comma Y. And the diameter of the graph is the maximum of all distances between vertices. Okay. Now, what do we mean by a fast network? Again, the network, we want to control this diameter. But if the number of vertices grow, naturally controlling the diameter will not be, it's not like saying all the diameters are less than equal to some number 5 or something like that. That may not make sense. But what we do require is that the diameter should be small relative to the number of vertices in the graph. Okay. And I will denote it sort of imprecisely by this equation here, that the diameter of G should be somewhat controlled by the number of vertices in the graph. Okay, and later on I will give you a theorem which will say that the best possible is that the diameter should be approximately the log of the number of vertices. Okay, and again I will make that also precise. So broadly, if we want a fast network, we will want a network where the diameter of each graph is approximately log of the number of vertices in that graph. Okay, this is what we will mean by fast. It won't be clear why this is fast precisely, but I hope everyone agrees that for a network to be fast, we want to control the diameter. Okay, and if you start with that idea, then slowly you will arrive at this kind of notion, simply because you want to increase the number of vertices while also keeping each network fast. So these are again somewhat contradictory requirements. You want it to be fast and you want more and more vertices. So this is the most appropriate definition for such a thing. Okay, so now that I have made some of those requirements somewhat precise, how do we measure reliability? Okay, so what we want to do, like I mentioned earlier, is to avoid situations where what I told you earlier, like you have 2 big cities which are connected by a single highway. Then all the traffic between the 2 cities will have to go through that highway. And which means if there is a problem on the highway, if there is a traffic jam on the highway, then the 2 cities will get badly disconnected. So we want to minimize such bottlenecks, as they are called. Okay. Bottleneck is the thin part of the bottleneck. So we want to avoid that situation. For that, what we do is the following. You take a subset of vertices, okay, not necessarily all the vertices, some small set, and you sort of think to yourself how well connected that subset is to its complement. Okay, so you break the set of vertices into two parts, one which I'm calling F and the other is V minus F, and you look at what is called the boundary of F, which is the edges that have one vertex in F and the other vertex in V minus F. Okay, this is called the boundary of F, and it's kind of obvious by symmetry that the boundary of F is the same as the boundary of its complement. Okay, and what we want to do, roughly speaking, is ensure that the cardinality of the boundary is reasonably large. Okay, in other words, given any subset F of the vertices, the number of edges which are connecting F to its complement should be reasonably large. Now, once again, when you say reasonably large, if I reduce the number of vertices in my set, naturally the number of edges coming out of it will also reduce. So we don't want the edges to be, this boundary to be absolutely big, but we want it to be big relative to the cardinality of both F and V minus F. Okay, so what we want is this ratio mu of F, which is the cardinality of the boundary divided by the minimum of the cardinalities of F and V minus F. That should be large enough, and I will explain what I mean by large enough in a second. So, roughly speaking, you want every subset of the vertices to be well connected to its complement. Okay, this will ensure that the network is reliable. This is broadly the idea. Now, this will lead us to the next notion, which is how do we really nail this down? In the previous slide, I had taken every subset of the vertices and wrote down a ratio. In order to ensure that these ratios are all large enough, we now look at what is called the isoperimetric constant. Okay, what you do is you take every subset of the vertices F and you look at this ratio, which I called mu of F on the previous slide, and you take the minimum over all F. Okay, now this thing is called the isoperimetric constant. Roughly speaking, if you know this number, then you know how reliable your network is. It gives you a precise measurable number which allows you to detect whether a network is measurable or not. Okay. Now, a small word on why this is called the isoperimetric constant is if you just sort of break this definition apart, you will see that for any subset F of V, you have this kind of inequality. That is, the cardinality of the boundary of F is greater than or equal to H of G times the cardinality of F. Okay. In other words, the cardinality of F is controlled by the cardinality of its boundary. Okay. So if a subset is large, its boundary will also be large, is what it's trying to say. Okay. And this kind of inequality is typically called an isoperimetric inequality in other parts of mathematics. You may have heard this term before. The simplest phenomenon is if you draw a closed curve in R2, then the area of the region enclosed by the curve is controlled by the perimeter of the boundary, that is the length of the curve. Okay, and this is a similar sort of statement. It says that the area, which is the cardinality of my F, is controlled by the cardinality of the boundary, which is like the perimeter. Okay, that's why this is called the isoperimetric constant. It has many other names, but we will stick to this one name. Now, what do we want? When we want a reliable, scalable network, what we want is to ensure that I want a family of graphs, Gn. Moreover, there should exist a single number R, which is independent of n, such that all of these Gn's have isoperimetric constant greater than or equal to R. Okay. In other words, as you add more and more vertices, the network remains reliable. Okay. And moreover, it remains reliable in a predictable way. In other words, you know this R. You know that there is a lower bound on the R, which means that given a set F and you look at its complement, you can guess how many edges there are from F to its complement. Okay. So it gives you a predictable, precise way to measure reliability. So now is a good time for me to maybe stop and ask, are there any questions? Okay. If not,
there is one question by Professor Ajit. She's asking non-empty and non-full. I think, is it about F?
F, yeah, perhaps. Yeah, I may have been a little imprecise. Maybe you need to assume it's non-empty. But if it's empty, you can take the corresponding things to be zero. So yes, you probably need to assume non-empty first.
Thank you.
Yeah, absolutely. Okay, so now let us get back to our original requirement of the. Oh, sorry. Before that, let me give you some examples of this isoperimetric constant. Okay. So let us take a cycle graph, what's called a cycle graph. Namely, you have some number of vertices, in this case 6, and each one is connected to the next one in a cycle. Okay. So suppose I take F to be a singleton 1, then F is connected to 2 of its neighbors. So its boundary consists of 2 edges, and therefore mu of F is 2. If I take F to consist of 1, 2, then its boundary, remember the boundary is edges which have one vertex in F and one vertex outside F. So there are only 2 such edges. One is this 2, 3 and the other is 1, 6. So I have 2 elements in the boundary of F. So this ratio is 1. Similarly, if I take 1, 2, 3, I get only 2 edges in the boundary. So its mu of F is 2, 3. Okay. So this isoperimetric constant is the minimum over all these numbers mu of F. So it's less than equal to 2/3. And it turns out it's actually equal to 2/3. Okay. One can verify this. So this is the isoperimetric constant of the cycle graph. Now, let me give you another example. Suppose you take what is called the complete graph. Namely, you take some number of vertices and you connect all vertices to all other vertices. Okay. So in this case, I've drawn a picture of K6. This is the complete graph on 6 vertices. It is, let me remind you, a 5 regular graph. Namely, every vertex has degree 5. And now if you run through a similar argument, if I take F to be a singleton 1, there are 5 edges coming out of it. So mu of F is 5. If I take 2 points, then I will have, and I will leave it to you to check, 2 times 4 entries in this boundary. So the ratio will be 4. If I take 1, 2, 3 as my set, then I'll have 3 times 3 elements in the 9 elements in the boundary. So the ratio is 3. And so on. One can check for other sets. But this calculation itself tells you that H of K6 is less than equal to 3. And it turns out it's equal to 3. Okay. But just to give you a sense of it, suppose I take the set 1, 2, 3, and I look at the number of edges connecting this set to its complement, you will see that there are exactly 9 edges. And therefore, this ratio should be less than equal to 3. And it's not hard to imagine that it's actually equal. Okay. So the takeaway from this is, in the previous example, it was 2/3. In this case, it is 3. So K6 is better connected than C6. Okay. Which is not hard to imagine, because here, if I have to go from, say, 1 to 3, I have to pass through 2. Whereas here I can go directly from 1 to 3 and other things. If I delete an edge, then this will become disconnected. But if I delete one edge over here, this will not be disconnected. I will still be able to go from any point to any other. Okay. So K6 is better connected than C6, which is something to keep in mind in this context. Okay. So let us get back to this model of networks that we were trying to construct. We want a sequence. Remember, we want a scalable model. So we don't want just one graph. We want many graphs with a number of properties. The first property is that it should be a scalable model. Namely, that the number of vertices blows up. As n goes to infinity, the vertices also go to plus infinity. The second is it should be connected, namely every GN, every graph in this sequence should be connected. And connected means that any 2 points you should be able to walk from one to the other via a path. The third is it should be cost effective, which means controlling the number of edges. And like I told you earlier, in our case, it will mean that there exists a single D such that each GN is D regular. Okay? So D is fixed and it's independent of N. Then I want it to be reliable, which means that this isoperimetric constant should be bounded below, as they say. That means there should exist a positive number R such that H of Gn is greater than or equal to R for all. And finally, we want it to be fast, which in our case means that the diameter should be controlled, and more specifically should be controlled by the number of vertices. Okay. And like I said earlier, and I will make it precise shortly, the diameter should be approximately the log of the number of vertices. Okay, that is what we mean by fast. Now, there is one simplification one can make over here, which is not entirely obvious when you first look at these conditions. It turns out the fourth condition implies the fifth condition, which is what I want to talk about. Reliability implies that this network is fast. Okay. And why is that true? The reason is, if I start with a D-regular graph and D is greater than or equal to 3, so some requirement, then the diameter of the graph is sandwiched between two numbers, both of which depend on the log of mod D. So you get diameter is greater than or equal to log of the vertices, and it's less than or equal to some number times the log of the vertices. Now, in order to ensure that the diameter is small, it suffices to kind of ensure that this inequality, the sequence of inequalities is best possible. Now, how do you optimize it? The only thing in your control is H of G, which appears on the right-hand side of this inequality. So, if we assume that you have a sequence Gn and there is an R positive such that H of Gn is greater than or equal to R, then the constant on the right-hand side is controlled by a single number. Because H of Gn will be greater than or equal to R, so whatever is inside this logarithm will be greater than or equal to 1 plus R by D. So you put a log, that inequality is preserved, and then when you take a reciprocal, that inequality is reversed. In other words, this whole constant that appears over here is controlled by 2 divided by log of 1 plus R by D. Okay. In other words, if you ensure that H of Gn is bounded below, then the diameter of Gn is the same order as the log of mod D. It's approximately the log of mod Dn by this pair of inequalities. So if we ensure in the previous slide, if we ensure that the network is reliable, then it's automatically fast. Okay, fast in the sense that the diameter is controlled. Reliable in the sense that the isoperimetric constant is bounded below. Okay. If this isoperimetric constant looks a little mysterious, leave it be. Just think of it as a way of measuring when a subset is connected to its complement in the set of vertices. Okay. So this is a somewhat unexpected result to have, but it allows us to simplify our requirement. So to conclude this section, what are we looking for? We are looking for a sequence of graphs Gn, which will now be called an expander family, if it satisfies 4 conditions. It's scalable, it's connected, it's cost effective, and it is both reliable and fast. Okay. And in our situation, it means that there should exist a single number R such that H of Gn is greater than or equal to R for all. Okay. Such a family of graphs is called an expander family. Okay, it roughly speaking models a good network for certain values of good. Okay, and we have tried to analyze what good might mean. And I hope everyone will agree that these are, I mean, if a network satisfies these conditions, then it would certainly be a good. Okay, so I've given you a definition. Now the question is, can you construct examples? And let me start with a non-example. Suppose I start with the cycle graph Cn. Namely, I put a bunch of vertices. In this picture, I put 8 vertices, and each one is connected to the next by a edge. We had seen earlier that h of C6 is less than equal to 2 by 3. It turns out h of Cn is less than equal to 4 by n. Okay. In other words, it's controlled by the number of vertices, but not in a good way. Namely that the vertices are down at the denominator, which means that h of Cn goes to 0 as n goes to infinity. So these cycle graphs do not form an expander family. Because remember, one of the conditions is we want these h of Cn's to be bounded below. There should exist an R such that h of Gn is greater than equal to R for all n. So while each of these is a non-zero number, the numbers are going to 0, which means as I grow my model, it's no longer going to be a reliable model. Okay, and that's evident over here in the sense that if I cut off one edge and I cut off another edge, I'm left with 2 disconnected pieces, which is not great. And moreover, if I cut off one edge, my network slows down significantly, because now to go from 1 to 2, I have to go all the way around the graph. Okay, so it affects both the reliability and the speed. And we have seen that reliable implies fast. So it's not surprising that both are affected. Okay, so this is why the cycle graphs do not form an expander family. What about the complete graphs? So last time I had shown you case 6. The idea is the same. You put down a number of vertices, in this case 8, and you connect all graphs to all, all vertices to all other vertices. In this case, we had seen that h of k6 was equal to 3. And in fact, h of kn is approximately n by 2. So it's large. Okay, the isoperimetric constant is large. In fact, it's growing as n goes to infinity. So it's certainly a reliable network and therefore a fast network, because I can go from any vertex to any other vertex in one edge. So it's fast. But the problem is, it is not a cost-effective model, because as my n grows, my degrees also blow up. K8 is a 7 regular graph. K15 is a 14 regular graph. So it means that I will need more and more edges in order to grow my network, and therefore it becomes prohibitively expensive. I can't have 10,000 people all living on a complete graph, because I will need that many -1 edges for each person, and that's too expensive. Okay. So these are 2 reasons why graphs, or rather sequences of graphs, would not form an expander family. It's because one of these conditions may break down. The complete graph is great if you want to literally connect 5 people to each other, but if you want a scalable model, it's not very good. And something similar for the cycle graphs is that it's fine for practical purposes for a small number, but as it gets bigger and bigger, it becomes less reliable. So you can have more bottlenecks, and therefore your network may break down more easily, which is not desirable for larger networks. So I've given you 2 non-examples. So the question is, do examples even exist? And this is an interesting problem. So it turns out expander families do exist. And indeed, for each d greater than equal to 5, there is a sequence Gn of d regular graphs that do form an expander family. And this was proved in 1973 by a gentleman named Pinsker. But the proof is interesting. It doesn't actually construct a graph or a sequence of graphs. It proves it using probability. It tells you that for each d greater than equal to 5, most graphs are expander families. Most sequences are expander families, which is a funny way to construct expander families, because it doesn't allow you to actually construct anything. You just know that it exists. I will talk about references later towards the end, but this book by Kowalski is a nice place to look at the proof. But now let me talk about an actual example. How do you construct an example? It turns out there is one way to do it, and Margulis did this in 1973, pretty soon after Pinsker's paper. And the proof uses group theory, which is what I want to discuss today. But before I go there, I should say that this is not the only way to construct expander families. There are many other ways as well. But this approach is very interesting because of the group theory. So let me talk about it. Once again, if there are any questions, please stop me. Let me now talk about Cayley graphs of groups. So what is...
question.
Yeah.
So you said reliable implies fast. What about the converse?
No, the converse is not true. Yeah, I would have to think of an example, but the converse is not true unless you make it very precise. So let me show you that inequality. It relies on this inequality, which tells you that if the isoperimetric constant is bounded below, then the diameter is approximately the log of Bn. But the converse is not necessarily true. It can happen even if h of Gn somehow goes to 0. But I can't think of an example off the top of my head. So the converse is not true.
Okay, thank you.
Sure. Okay, so let me get back to groups. So I hope everyone here knows what a group is. We'll fix a group and we'll take a subset S. And I will want the subset to satisfy two conditions. The first is that it should be symmetric, namely that whenever X is in S, X inverse is also in S. And the second is it should be a generating set, which means that for any X in G, I can find finitely many elements in the generating set, in the set S, such that X is the product of those finitely many elements. Okay. This K, the number of elements can vary depending on the element I choose, but I should be able to generate the entire group from S. And some useful examples of such sets are if I take G to be the integers, I can take S to be 1 and minus 1. Now the set 1, singleton 1 itself generates, but it's not a symmetric set, so I will want symmetric sets. If I take Z mod NZ, then the similar set, namely 1 and minus 1, will also be a symmetric generating set. If I take G to be the dihedral group, which is generated by two elements, R and S, R denotes the rotation and S denotes the reflection, then S can be, one example of S is R, R inverse, and S. This will form a symmetric generating set. If I take G to be the symmetric group, Sn, then I can have a generating set which consists of three elements, which is symmetric. Namely, I take one transposition, I take the n cycle, and I take the inverse of the n cycle. Okay. So these are all examples. I hope most of the viewers are familiar with these examples. These are common groups that you will encounter at various points in life. So this is what these are the kind of examples I have. Now, suppose I take a group G and I take such a symmetric generating set. Turns out I can draw a graph. What do? I take the vertices to be all the group elements. So each group element is one vertex in the graph. And I draw an edge if I can go from one to the other by one of the elements in the generating set. Okay. Namely, I draw an edge x comma y if there is an S in S such that x is S times y, which is the same as saying xy inverse belongs to S. Okay. Now, I just want to point out that because this is a symmetric generating set, if there is an edge from x to y, there is an edge from y to x. Okay, because this I can take an inverse of this expression. So if this is an undirected graph, it's called a Cayley graph. Okay. Now, the Cayley graph, I should mention here, depends not only on the group, but also on the generating set. Okay. Now, why do I want it to be a generating set? It's because I want the graph to be connected. Namely, if I take any two group elements, then there should be a path connecting X to Y. And for that, if you sort of break it down, you will see that it precisely means that this S should be a generating set. Because you want X, Y inverse to be a finite sequence of edges, and each edge, roughly speaking, represents one element of this generating set. Okay. So if you start with a symmetric generating set, the Cayley graph is an undirected graph which is also connected. Okay. This is the kind of thing we are looking at. Some examples. If I take G to be Z and S to be 1 minus 1, then the Cayley graph can be represented as a long line where each element is connected to, has two neighbors, namely +1 and -1 of that element. If I take G to be Z mod 6Z and S to be 1 minus 1, then the Cayley graph is a cycle. Why? Because every element has again two neighbors when I do +1 and -1. But when I come around to the last element, the last but one element, if I add 1, I get 0. So it's a cycle. And more generally, if I take Z mod NZ and the same generating set, then the Cayley graph is precisely the cycle graph that I drew earlier. Some other examples, if I take G to be D3 or S3, the symmetric group on 3 letters, and I take S to be this generating set, then with a little bit of work, you can draw the Cayley graph. Just keep in mind that the Cayley graph will have 6 vertices, and each vertex will have, in this case, 3 edges coming out of it, one for each generator. Okay, I'll say something more about that in a second. So it has, each vertex will have degree 3. But the same group with a different generating set can have a different Cayley graph. Okay, I can take S prime to be 1, 2, and 2, 3. This is also a generating set for S3. But the Cayley graph now looks very different. For one thing, this graph is 3 regular, but this graph is only 2 regular. Okay, so they are definitely not isomorphic graphs. So just keep in mind that the Cayley graph depends on both the group and the generating set. But there is one thing that one can say for sure, which is that the Cayley graph is regular. Why? Because if I take any vertex, then if you stop and think about it, there is an edge coming out of it, one for each member of the generating set. Okay, so it is D regular, where D is the cardinality of that set S that you started. Okay, so remember, we are looking for regular graphs. So this gives us a recipe to construct such regular graphs. Now, what are we going to do with this? Suppose you take now a finitely generated group. The group itself might be infinite, take Z or something like that. And you take a finite symmetric generating set. Then, if I take a normal subgroup of the group, I can turn the quotient into a group. Moreover, let's say I assume that this S, the symmetric generating set, does not intersect my subgroup at all. Then when I take the set S and I move it down to G mod H under pi, it will give me a set with the same cardinality because I have not lost anything when I take the image of S under pi. So I can construct a new Cayley graph of the quotient group with the image of the original generating set. But since the image also has the same cardinality as S, this graph is also deregular. So this gives us a way to construct many graphs. Remember, we want to construct a scalable model. So we want to construct a family of graphs. So what one can do is start with a single group G, a single generating set S, and then vary the normal subgroups. For each normal subgroup with these conditions, I can get a Cayley graph, and this way I can get a family of Cayley graphs from a single group, which is the kind of thing we will want to do. Some examples, again, it's same as what I wrote down earlier. If you take the Cayley graph of Z mod 6Z, now treating it as a subgroup of Z, you will get the cycle graph and so on. So starting with a single pair Z, S, you can construct an infinite sequence of graphs. One for each natural number, you will get a cycle graph for each natural number. So the question I'm going to look at is the following. Suppose you start with an infinite group now and a finite symmetric generating set, and you take a sequence of normal subgroups Hn such that S intersection Hn is empty for all n. Sorry. You can use this to construct a family of graphs, a sequence of graphs, which are given by the Cayley graphs of G mod Hn with the image of that same generating set. And because of this condition that S does not intersect Hn, all of them are D-regular for the same D, which is one of the conditions we wanted for our network. Now, an example here is if I take G to be Z and S to be 1 minus 1, Hn is Nz, then you get the quotient Cayley graphs to be the cycle graphs. So they don't form an expander family. So the question is, can you use this method to construct an expander family? And this is where Margulis's work comes in. The answer is yes. Specifically, one has to take certain kinds of groups. I'll talk about that in a second. But let me give you an example. Suppose I take the group SL3Z. If you have not seen this group, this is an interesting group. It's made up of matrices, 3 by 3 matrices, whose entries are integers and whose determinant is 1. Okay, this is a group, one can check this, and under matrix multiplication. And moreover, it's a finitely generated group. It's generated by 2 elements, namely this matrix and this matrix. Okay? All this requires a proof. From this point on, I'm going to necessarily be a little vague and a little fast, but please bear with me. The idea is this is a group for which I know that I can construct expander families, and I want to tell you how that works. So suppose I take S to be this generating set. It has 2 elements. I can proceed this to this method. What I do is I take quotients of SL3Z, namely I take SL3Z mod NZ. Namely, I take all 3 by 3 matrices where AI are integers modulo n with the same condition on the determinant. And I have a natural surjective homomorphism from SL3Z to SL3Z mod NZ, which literally takes all the entries and goes modulo n. Now, when I go mod n, this set S is not affected. Namely, the set S is not in the kernel of this surjective homomorphism. Therefore, I can take the Cayley graphs of all these quotients. These are all 2 regular graphs because this S and therefore all these pi n of S's have 2 elements each. So these are all 2 regular graphs, and now I have a sequence of 2 regular graphs. And Margulis proved that if I take these xn's constructed from this one group, it forms an expander family. Okay. So I hope the statement of the theorem is clear. Now let me explain why it is true. What is special about SL3Z? We saw that for Z, this doesn't work, right? If I take the group to be Z, then the quotient graphs are all cycles, and that doesn't form an expander family. So there's clearly something about this group that's making this happen. So the question is, what is that? Turns out it's related to some representations. Now, a quick word on what representations are. If I take a group G and a vector space V, a representation is a homomorphism from the group to GLV, namely the group of all invertible linear operators on V. Okay. GLV is a group under composition of operators, and we want this to be a homomorphism. You should think of a representation as a group action of G on a vector space. Okay, that's what a representation is. So if you've seen group actions, you can sort of guess what this would look like. I have given some examples, but maybe in the interest of time, I will skip these examples. You can take any homomorphism from G into matrices, and that will give you a representation. Okay, so many groups will admit representations. In fact, all groups do. And it's an interesting subject to study the representations themselves. But let me say a little bit about what I want to talk about. I want to talk about certain kinds of representations, namely representations not on any vector space, but on a Hilbert space. So a Hilbert space, if you're not familiar with it, is just an inner product space with some additional structure. Okay. So an inner product would mean that you have this bilinear map with certain conditions, or conjugate linear. And what's important over here is that the Hilbert space is not just an inner product space. Because it's an inner product space, it also is a metric space. Namely, I can measure the distance between two vectors by looking at this number, the square root of x minus y dot x minus y. Okay. Moreover, it should be complete with respect to this metric. If you have not seen Hilbert spaces, maybe just take them to mean some sort of inner product space. Okay, that's good enough. Now, the kind of representations I want to talk about are what are called unitary representations. So a representation is unitary if for every element of the group G, rho G, which is the image of G under this, remember it's now a linear operator on H, that should be a unitary operator. Namely, it should preserve the inner product. Rho G of x dot rho G of y should be the same as x dot y. And this should happen for all x, all y, and all g. Okay. So a unitary representation, remember a representation is a group action of G on a vector space. A unitary representation is a group action of G on a Hilbert space. Because on a Hilbert space, you have this added structure of an inner product, and you want to preserve that inner product when the group acts. So that's what a unitary representation is. It's a fairly natural thing to look at for, especially for infinite groups, which is the context we are in right now. What I want to say is that the reason SL3Z allows you to construct expander families is because SL3Z has a certain kind of representation to it. Namely, it is somewhat rigid. Okay? And I'll say what I mean by rigid in a second. So suppose I start with a unitary representation. I take a finite set K and an epsilon positive. I say that a vector X is epsilon K invariant if whenever, sorry, this should be S in K. There's a typo here. If I take an element S of the subset K and I apply rho S to X, it should not move X by too much. That's what this inequality is saying. Okay. For every S in K, the amount it moves X by is not much. It's controlled by the norm of X, the distance of X from C. Okay. And such a vector is called an epsilon K invariant vector. The simplest example of this is an invariant vector. Namely, a vector Y is invariant if rho G of Y is equal to Y for all G. So the group action can have fixed points or, vectors that are not moved by the group action. Such vectors are called invariant vectors. An epsilon K invariant vector is an almost invariant vector. Okay. It gets moved, but not by too much. Now, the property that SL3Z satisfies is an interesting property from the point of view of representation theory. A group G is said to have property T, and this is somewhat technical, but just bear with me. If there exists an epsilon and a K with the following condition. Suppose I take any representation and it contains a non-zero epsilon K invariant vector, namely a vector which is not moved too much, then it must contain an invariant vector. Okay, it's not saying that that epsilon K invariant vector is already an invariant vector. It's just that you can construct another one. In other words, the representations are rigid, meaning that if a representation does not have any invariant vectors, that means it cannot have any almost invariant vectors either. Which means that if I take a vector X, it has to be moved some precise distance. it has to be moved at least epsilon distance from where it started. That's what property T means. It means that if you start with a representation that does not have invariant vectors, which one can construct, they are called irreducible representations. The moment you have such a representation, it has to move points around, and moreover, it has to move them by a prescribed distance. Has to move them at least by epsilon. Okay, so it has rigid representation theory. That's roughly what property T means. Some examples. Every finite group has property T. The moment you have epsilon k invariant vectors, you can kind of average them out and get an invariant vector. Epsilon has to be less than 1. SL3Z has property T. I'm not going to prove this at all, but there are proofs available in 2 books, and I'll talk about references when we get there. There are groups, of course, that do not have property T. They all must be infinite groups because of what I mentioned on the top line. Z is the first example of a group that does not have property T. In other words, the representations of Z are not rigid in this sense. Okay. Indeed, no infinite abelian group has property T. SL2Z, namely, if I take the same sort of matrix group but with the 2 by 2 matrices, it does not have property T. So you need to have 3 by 3 matrices. And there are many other groups that do not. One example is the free groups. Namely, I take n elements and I just take all words that I can build out of those n elements. That's a free group and it does not have property T. There is a small fact that allows you to discount other possibilities. Namely, every group with property T has to be finitely generated. Namely, it has a finite generating set. And therefore, there are some groups which you can ignore. But these are some interesting examples. SL3Z has property T. And what Margulis proved was the following, that if you start with a group which has property T, and S is a finite generating set, you can use it to construct expander families. Namely, you choose a sequence of normal subgroups, and suppose you can choose it such that S intersection Hn is empty, and each Hn has finite index. So the Cayley graphs of the quotients are all finite graphs, but the index blows up, which means it's a scalable model in the sense that we talked about. Then these Cayley graphs of G mod Hn with the image of the same S form an expander family. Okay. So this is, of course, a hard proof. It's not easy. I will not give you a proof, nor will I tell you why it is true in any deep sense of the word, other than the fact that somehow the representation theory of the group affects this kind of property. Okay. So let me conclude. What we are after in the theory of expanders is a graph that will be a good network, or rather a good family of networks. And by good, we mean it is cost effective, connected, fast and reliable. And we made all those notions somewhat mathematically precise. Reliable and fast are both dependent on the isoperimetric constant, and indeed reliable implies fast. And an expander family is a scalable model of such networks. Namely, it's an infinite sequence of d-regular graphs whose vertex sets are blowing up, namely the number of vertices is going to plus infinity, but whose isoperimetric constants are bounded below. Therefore, the family is uniformly reliable and uniformly fast. Now, how do you construct such expanders? Turns out you can construct them using Cayley graphs of certain groups. Specifically, you can start with a group with property T, an infinite group with property T, and you can take a generating set, a finite generating set, and under certain conditions, if you can construct certain subgroups, these subgroups Hn on the previous slide, which have finite index but whose indexes are growing, then you can use it to construct an expander family. By the way, such groups are typically called residually finite groups. Groups which have families of subgroups with this property. Okay. So one example of this entire phenomenon is SL3Z. Indeed, SLNZ for all n greater than equal to 3 will allow you to form such expander families. So that's the end of my talk. Let me just give you a few references. There is a book by Kowalski on expander graphs where he gives that first probabilistic proof that Pinsker had given. He describes it in some detail. There is an excellent book by Krebs and Shahi where they talk about expander families and Cayley graphs and how you use them. They talk about this property P and all these things. There is an older book by Alexander Lubotsky. Lubotsky was one of the pioneers in this field in the 90s, and he wrote a very nice book around the time when the field was really exploding. And it's a book that's worth reading. You learn a lot about, especially about representation theory. And Terence Tao gave a series of lectures, and then he compiled it into this book on expansion in finite simple groups of real type, which is now published by AMS. That is also worth reading. But my personal recommendation is to read the second book by Krebs and Shahi. It's a fabulous book that I think everyone should at least take a peek at. It's a very interesting subject. So I will stop here. I'm sorry if I ran over, but thank you very much.
Thank you for being so patient with us, everyone. Now we would like to open the floor for the questions. If you have any queries, please feel free to type your questions in the Zoom chat box or use the raise hand feature. In case YouTube viewers have any questions, please feel free to drop your questions in the chat box. We will convey your questions to the sir.
Yeah, please go ahead. I can see some hands.
Mandeep?
Good evening, sir.
Yeah.
Am I audible?
Yeah, you are.
Okay, so my question is, you told that SL3Z is generated by the two matrices that you mentioned. So can you give some sketch of proof or some idea that how you found those generators?
Not off the top of my head. I don't know. I would have to think. I don't know off the top of my head, but I can tell you a place you can find it on Terence Tao's blog. So that is an easy place to find it. He has some notes on the SLN groups. I believe Lubotsky's book will also have a proof. I'm fairly certain. There are many generating sets for SL3Z, and in a sense, it doesn't matter which generating set you take for this kind of theory to work. But I believe this set with two elements is, naturally, it's optimal. There may be other, but I can't think of a proof directly off the top. Sorry.
Okay, thank you, sir.
So for the other SLNs, do you again have only two generators or more, right?
Well, there are three, but I believe it's possible to reduce it to two. But there is a finite generating set, that's for sure. And I think you can write down three matrices that generate. There is an very old paper, I think it's from the 50s, where they actually proved this. But my resource would be Lubotsky's book, where he describes the generating sets and things like that. But I know that three matrices is good enough to generate a set.
Yeah, okay. Any other questions?
I think there are no questions. We can go ahead. So
Yeah, over to
now,
Bhumika. Okay, Asta, please.
so now it's time to capture a glimpse of this talk. I request everyone to turn your cameras on for a group photo.
Okay, so on the countdown of 1, 2, 3, we will capture a group photo. So let us wait for a few more seconds. Okay, so shall we take the group photo now? Yes, Soumya sir? Okay, fine. So 1, 2, 3. Okay, thank you. We are done.
On the behalf of Current team, I would like to extend our heartfelt thanks to all of you for your active participation and enthusiastic engagement in this event. We are immensely grateful to Dr. Vaidyanathan for his insightful presentation, which has enriched our understanding of our expander groups and graphs. We would also like to thank MTTS Trust and the team of entire organizing team whose hard work and dedication has made this event possible. As the event comes to a close, we kindly ask all our participants to log out of the Zoom meeting. Your presence has made this event a great success, and we look forward to your continued support.